Hello everyone, welcome to the INQA seminar series. Today with us we have Maxime Dupont from Rigetti, who's gonna tell us something about QAOA. Please begin.
Yeah, well, thanks for inviting me to the talk. Hi everyone. So yeah, I'm going to talk about an algorithm that we developed for solving combinatorial optimization problems using quantum computer or quantum annealer. But yeah, most of the talk will be about like the QAOA aspect of it, but we'll discuss a bit quantum annealing. So when we say combinatorial optimization, the goal is to extremize a function defined over discrete variables. And what we mean by that is that, well, instead of the variables of the function being any real numbers, they can only take values, let's say plus minus one, for example. And this kind of problems arises in many contexts of science, such as statistical physics, condensed matter, biology, but also in everyday life, since this has to do with problems connecting to logistics, scheduling, finance, and so on. And so in this presentation, I'll be focusing on a specific type of combinatorial optimization problem, which are quadratic, unconstrained, and binary. And well, if you're coming like me from a physics background, this is a fancy way of finding the ground state of a classical Ising model. Both problems are strictly equivalent. So we have Ising spins, which take discrete values plus minus one. And then we have two-body terms interaction between them. And so we can picture that problem as a graph where the nodes are the variables and the edges, the interactions. And so our problem is defined as a graph, which is defined by an adjacency matrix W. So solving a generic combinatorial optimization problem is hard with no method that will guarantee finding the optimal solution in finite time. So there is a zoo of solvers that have been developed for classical computers. And some of the most competitive solvers are simulated annealing, parallel tempering, branch and bound. And while I don't want to spend too much time on those because the title of the talk is Quantum, Relax, and Round. And so let's focus on relaxed methods in the classical context before moving later to the quantum analog version that we developed. So relaxed methods often relate to semi-definite programming solvers. And usually those solvers are able to provide a lower or upper bound for the optimal solution. And as such, they provide performance guarantees on the quality of a solution. And a famous example is the Goemans-Williamson algorithm for solving the maximum cut problem. And it mathematically guarantees to find a solution which is 88% close to the optimal one. So what do we mean by a relaxed method? So I'm giving here a very simple example. We have our objective function defined over n discrete variables. And if we relax the domains of those variables to, let's say, to real numbers, well, then the objective function is easy to solve. This is just an eigenvalue problem where one needs to find the leading eigenvector of the adjacency matrix W. And we know how to do that efficiently. So, of course, the solution we get is not valid with respect to the original problem. And so we need a rounding step that is going to bring us back to the space of valid solutions made of plus minus one. And a very simple strategy for achieving that is just to sign round the entries of the leading eigenvector to plus minus one. Very easy strategy in the end, and it works relatively well, but of course it won't give the optimal solution. So after classical algorithms, I want to tell you a bit more about the quantum side. And the first one is quantum annealing, and it does not need to be introduced to this audience. And it's particularly well suited for analog quantum computers. A second class of quantum algorithms are variational quantum algorithms used in the context mostly of gate-based quantum computing. And we'll come back to that in the following. But this is related, for example, to QAOA, which stands for Quantum Approximate Optimization Algorithm. And finally, I want to mention that there are other approaches. I just want to mention them: quantum works, Grover type search algorithm, and so on, that have also been developed on the quantum side. So quantum annealing, again, doesn't need much of an introduction. So let me briefly introduce the idea behind variational algorithm instead, because we'll use those in the following. So the idea is to have quantum circuits parameterized with angles theta. And now the goal is to find or optimize those angles such that the output of the quantum computer does the job we want. And in the context of combinatorial optimization, this job means extremizing, let's say, the average objective value of the output bit strings, where each of them corresponds to a candidate solution to our problem. And so that's the basis of variational quantum algorithms. And QAOA is one of such algorithms. And in particular, well, the variational quantum circuit that we use could be anything in principle, but we can be smart about it, and it can be inspired by other methods which work well, and that's the case for QAOA. So first, we have an n-variable binary solution, which is mapped onto a length and bit string, and each of those bit string is a candidate solution with a cost corresponding to the objective value of that bit string. And the quantum circuit for the QAOA is inspired by quantum annealing. But it corresponds to one, a discretized version of it, and two, instead of having the angles of the unitaries fixed by a chosen interpolation strategy between initial and final states, these angles are parameters being optimized to extremize the expectation of the objective value from the sample bit string. So let's give an example here where the problems we consider are all-to-all graphs with weights ±1 at random. And this corresponds to a Sherrington-Kirkpatrick spin glass problem. So we have a variational circuit, let's say, with only two parameters. And two parameters to optimize mean we can make a plot with a landscape of the average objective value as a function of these two parameters. And we have optimal angles when we minimize this objective value on average. And at those values for the angle, well, we'll get the best possible solution from the algorithm on average. Of course, these solutions may not be the optimal ones with respect to the problem that we have at end, but they are the optimal ones given that we only have a quantum circuit with two parameters. So after this overview of classical and quantum algorithms, we have everything we need to get to the core of this presentation, which is a quantum relax and run solver. So here's what we propose. First, run a typical quantum heuristic algorithm for solving the input quadratic unconstrained binary optimization problem of interest. And this means running, as usual, quantum annealing or the QAOA. Second, sample bit strings and compute a correlation matrix Z. And what we suggest is to perform a relax and run strategy on the correlation matrix instead of the adjacency matrix. Why should that even do anything meaningful? Well, there is an intuition. If we have negative weight Wij between two spins, this will tend to make them align to minimize the energy. And this means that the correlation will be negative too, because we have an extra minus sign in the definition. So there is similar information in W, and z. And it's kind of visual from the two matrices on the slide. So now I want to say that, is there a benefit of doing that? And yes, there is, at least like a very theoretical one, which is that if the underlying quantum algorithm that we use returns the solution exactly, so if quantum annealing or QAOA just like output bit strings which are all optimal, while the relax and round step will also return the optimal solution. So good, but of course that's an extreme case. The quantum algorithm is a heuristic, and which is unlikely to solve the problem exactly anyway. So the question is, what happens for the quantum relax and round solver then if the underlying quantum algorithm doesn't solve the problem exactly? What is the benefit of doing that extra step of building the correlation matrix and then doing a relax and round step on that? So let me start showing some data. First, we're going to focus on those Sherrington-Kirkpatrick spin glasses, and we will do that with the QAOA to generate the correlation matrix. So we have the 3 steps: run QAOA with 2 p parameters at optimal values. We compute the correlation matrix from sample bit strings, and then we do a relax and round on this correlation matrix. So here is a plot of the normalized objective function value as a function of the number of variables n. And each data point is averaged over thousands of randomly generated problem instances. The circles, they correspond to the classical relax and round method on the adjacency matrix of the graph problem directly. The other markers or symbols, they correspond to the quantum relax and round version from p = 1 to p = 16. So with more and more variational parameters in the QAOA. And we observe that by increasing the number of variational parameters, we do better and better, given the objective function needs to be minimized. So the optimal value with n goes to infinity, we know it analytically for Sherrington-Kirkpatrick spin glasses, it's the Parisi value. We also know analytically the performance of the QAOA algorithm at p = 1, and it gives an average objective value of about minus 0.3. We know analytically that QAOA at p = 11 is needed to achieve as well as a classical relax and round strategy. Here we observe that while the quantum relax and round based on the QAOA at p = 1 achieves as well as a classical relax and round solver, and so as well as the QAOA at p = 11. So what it means that embedding the QAOA at p = 1 into a relax and round strategy does much better than the QAOA alone with the same number of variational parameters. So from there, if we look a bit more closely at this plot, we see that the classical and the quantum relax and round at p = 1, they suspiciously match each other in terms of performance. Like the black crosses are perfectly on top of the circle. And can we understand that? Yes. In fact, we can show analytically that the classical and quantum relax and round algorithms at p = 1 gives the same solution in the large n limit. Here is a sketch of the proof. We first compute the correlations at optimal angles analytically. We can do that at p = 1. Then we show that the correlation and adjacency matrices, they commute in the large n limit. And while if they commute, it means they share the same eigenspace, and it means they share the same eigenvectors. And because the eigenvectors are the solutions to the relax problem, they share the same solutions at p = 1. So at p = 1, we do as well as a classical relax and round. And by increasing p, the number of variational parameters in the QAOA, we do better. So before extending the analysis to more problems and plugging in quantum annealing instead of the QAOA, I want to stop with this slide on some properties of the algorithm. The first thing is that we work with expectation values rather than bit strings directly. And those are much more robust quantities given their average over many bit strings. And if we think of a depolarizing noise model, where the quantum state is a mixture between the pure state and the fully depolarized state, well, the quantum reaction-1 algorithm is robust to that. Why? Well, because the effect of such a noise channel on the observables we need to compute to build the correlation matrix is just a rescaling. And when it comes to finding the eigenvectors of a matrix, this is irrelevant whether the entries are rescaled by a factor or not, if this factor is the same for everyone. And thanks to that, well, we expect some sort of robustness to noise for this quantum reaction-1 algorithm. Another related thing is about the number of bit strings we need for computing the correlation. In the end, we need to find the eigenvector of a matrix. And because we only have a finite number of bit strings, this will induce noise in the correlation matrix entries. And how robust is finding the leading eigenvectors if there is noise in the matrix because of a finite number of bit strings that we use for computing expectation values. So we did numerical simulations on Sherrington-Kirkpatrick spin glasses. And on that plot here, I plot the average objective value as a function of the number of bit strings. And the more they are, the better the value until it converges. We see that like those curves plateau for a large number of bit strings. So now we can say a bit more. How? Well, the first thing we're gonna do from going from the plot on the left to the plot on the right, they both have the same data points. The data is the same, it's just plotted differently. The first thing we do is that we normalize the y-axis by the objective value with an infinite number of bit strings. That's what we do on the y-axis, and that's why like the maximum value it can take is 1. Then the second thing we do is that we multiply the x-axis by n to the power minus 3 half. And if we do that with this value minus 3 half, well, we find that all the data points seem to collapse onto each other. And we don't really have an explanation for that or like for why 3 half, but what it means in practice is that the number of bit strings that we need to achieve a given accuracy should scale polynomially with n. So two things right here, robustness to depolarizing noise, then studying like the effect of finite number of bit strings for computing entries in the correlation matrix. And one last thing that I want to mention on that side is the runtime of doing a relax and run step. So say we have run the quantum algorithm nx times to collect nx bit strings. This has been done. And now what we show here on that plot is a runtime in seconds to build the correlation matrix from those nx bit strings and find the leading eigenvector as a function of n. Building the correlation matrix, it has n square entries. Finding the leading eigenvector, it can be done in n square steps. And so we find indeed that like these curves in the large n limit have this n square scaling, which is like the dashed gray line. So this is something to have in mind when time to solution is a relevant metric, because a relax and run step adds runtime. Okay, let me continue with more data on our quantum relax and run solver. And I'm showing now the approximation ratio, which estimates the quality of a solution with respect to the optimal one. And we want this number alpha to be as close to 1 as possible. If it's equal to 1, it means we solve the problem exactly and found the optimal solution. So here we show the data that I presented before for the Sherrington-Kirkpatrick spin classes. And again, we can note these two things, that first, the classical and quantum relax and runs are on par at p equal 1. And the second thing to note is that we mentioned earlier that increasing p, increasing the number of variational parameters in the underlying quantum algorithm, increases the performance. In addition to that, within each of these bars, there is another bar with a darker shade. And this is the performance of the QAOA with P layers. And so we observe that the quantum relaxant round based on the QAOA with P layers performs better than the raw QAOA, while in the end, we just use the same information because for the relaxant round step, we just use data from the QAOA. So Sherrington-Kirkpatrick spin glasses here, and of course we can repeat that for as many problem classes as we want, and that's what I'm showing here. Without going into like the details of like each type of problem, the conclusion for those is similar to what I just said for the Sherrington-Kirkpatrick models. Classical and quantum at p = 1 are the same or very close in performance. And increasing p yields improving solution. Plus, from there, embedding the QAOA into a relax and run approach always performs better than the raw QAOA or QAOA itself. So in the end, we don't need any more information than what we already have to run a relax and run strategy, because when we run quantum annealing, all the QAOA, we sample bit strings, right? And so here, like from those bit strings, we can just compute a correlation matrix and then do a relax and run step. So it seems to come for free if runtime is not an issue here. So why not do it? So far I've focused on a specific relax and run strategy. There exist many, some of which are targeted to specific problems. One of them is for the maximum cut problem, where one seeks to maximize this objective function. And here the Wij are positive or 0. So it turns out that this problem is invariant if we add a diagonal to the adjacency matrix where the sum of the entries of the diagonal are 0. And this gives us extra freedom here because we can optimize this diagonal, which I call the correcting vector U. So we can write down U enhanced relaxed version of this problem. And the relaxed problem is an upper bound to the optimal solution here, to the maximum cut problem. So with the help of this extra freedom in the correcting vector U, we can minimize the upper bound to get closer to the optimal solution. And the way to read like this min-max equation is that the goal here is to minimize the maximum eigenvalue, which is an upper bound to the optimal solution. So this relaxed algorithm here is equivalent to the Goemans-Williamson algorithm, and it can be shown to guarantee a solution with a quality of about 88% of the optimal one. And here we suggest a quantum version of that, where we substitute the adjacency matrix for the correlation matrix. Okay, so what does it give? Well, here are numerical data on unit weight random regular graphs. And we see that the quantum at p = 1 and the classical Goemans-Williamson algorithm are performing on par similarly well. And that by increasing p, we increase the performance. And again, we see that within each of these bars, there is a bar with a darker shade, which just corresponds to the performance of the QAOA. And doing this relax and run step on top of the bit string sample from the QAOA will perform much better. So this is just a numerical result. We cannot show much analytically in that case. Nevertheless, it remains a powerful heuristic, with the baseline being that of a powerful classical algorithm at p = 1, and with a path for increasing the quality of the solution by increasing p. Okay, so it's been a lot about the QAOA so far, and so I want to show here that we can replace the QAOA by quantum annealing. And I'll do that by solving another type of problems, which is a maximum independent set on random unit disk graphs. And these graphs and this problem is relevant, let's say, for people working with Rydberg atoms, for example, like the Lukens group at Harvard. So here's a different step we perform. Run the quantum annealing algorithm for a total time t, and then we build a correlation matrix from sampling bit strings, and then we perform a relax and round step based on the correlation matrix. Now what I show is a plot with numerical data. So different symbols correspond to different problem sizes. The x-axis is the total evolution time t. The y-axis is the ratio of the objective value of the quantum relax and round and quantum annealing -1. Why is that? Well, when the total annealing time goes to infinity, both quantum annealing and quantum relax and round solve the problem exactly. So this ratio is equal to 1, and the y-axis goes to 0, which is what we observe here. What we observe at finite t, well, is that the quantum relax and round algorithm performs better than the raw quantum annealing. And this is a similar conclusion to what we've observed when using the QAOA before. Moreover, we observe empirically a relationship between the relative performance of quantum relax and round and quantum annealing and the total time t. With like this exponents we have. However, we don't really have an explanation for that, and we didn't really push this further. This is just an observation, and the main focus of that work was on the QAOA. So this is just the quantum annealing contribution to that work. But it seems to work with quantum annealing as well as with QAOA. And given that one samples bit strings when using a quantum annealer, it comes for free to try a relax and round strategy on the correlation matrix. Of course, there's always like the runtime addition because of these extra steps we do, but I think that would still be interesting to try that. So conclusion and next steps. Well, to conclude, we've introduced an algorithm extending relax and round solvers with quantum correlation. We show that they can be as performant as their classical counterparts in the simplest case, which was when using the QAOA with p = 1. But more importantly, we showed that the performance can be improved from this baseline by increasing the number of parameters p in the QAOA. There are several natural next steps, just putting a few here. The first one on the theory side, there are some things we can show analytically, but not all the time. And in that case, we rely on numerical simulations. And so a question is, well, can we provide more analytical results? Other next steps are on the experimental side. We've introduced an algorithm performing better than the raw QAOA. How does it perform in practice on noisy quantum computer? Well, then especially for this audience, it would be very interesting to look at whether there is a performance gain by using this kind of relax and round strategy with a quantum annealer. Of course, for quantum annealing, time to solution is an important metric, and we know that building the correlation matrix and finding its eigenvectors, this takes time. But I think it will still be good to see how this performs irrespective of time. And yep, with that, I thank you for your attention.
Thanks for the great talk. Are there any questions? Yeah, perhaps I can ask one. So you had your alternative strategy for one of the slides, but I guess I didn't really follow which part of the strategy is quantum and which part of the strategy is some classical post-processing or pre-processing.
Yeah, so I guess that's a strategy referred to, like that was for MaxCut. So here, like the algorithm, like everything that's displayed on that screen is purely classical. There is nothing quantum in what's displayed. The only quantum part is to just run this algorithm, but just substituting the adjacency matrix for the correlation matrix. So that's the quantum part, because the correlation matrix has been computed from a quantum algorithm. And then it's just running that as usual in post-processing. It's more post-processing step, yeah.
Got it, thanks. So if there are no further questions, then let's stop here and see you all next week.